well, we were discussing ideal solutions, and in ideal solutions we had I had already discussed the PXY diagrams which have been which is shown here, and then I had also discussed the TXY diagram, and these diagrams, they are particularly useful for describing the process of rectification, which is distillation a number of times, which we use very frequently in chemical engineering in order to separate two particular components with small differences in boiling point. When the difference is very large, then if we simply vaporize, we start vaporizing the mixture and then condense it, then in that case we can get a good enough separation. But when the boiling point differences are not very large, we need to repeat this process of boiling and condensation a large number of times. Let us see how this particular process works. Say suppose we have started with a liquid of composition. We start heating it. We keep on heating it till we reach the bubble point curve. Once we reach the bubble point curve and we start vaporizing, we find that the vapor composition is given here. We already find that the vapor is richer in the more volatile component as the liquid phase. Now we condense the whole vapor. What we do? We simply cool it. We do not do anything. And then again we start vaporizing. Moment we start vaporizing, the first vapor again we find it is richer than the liquid which we started, and it is much more richer than the liquid mixture which we had originally taken. Now suppose we keep on repeating this, we simply condense the whole thing, and again we vaporize it, right. This is the composition of the vapor. We simply condense the vapor and again we vaporize it. So in the process, what have we got? In the process we find that we have come to a liquid solution which is much more richer, almost which comprises of the pure component of the more volatile component, where we had started with a mixture which had much less proportion of the more volatile component. Now in this particular process is the basic principle underlying the process of rectification, which we will be learning in great details when you go further into your training of chemical engineering. So by this time, what are the things that we have done? We have dealt with PXY, we have dealt with PXY diagrams, we have dealt with TXY diagrams, and now from this TXY diagrams we find that locating the tie lines, we can generate the vapor and the liquid and the vapor in equilibrium with one another, and these particular compositions, they are then plotted in the x1 versus y1 curve. Now here I would like to mention one thing. Again I would like to remind that what is x1? x1 refers to the more volatile component. This is something very important that you need to remember throughout. You can perform the entire phase diagrams with the less volatile component. The only difference is the curves will be just, they will just be reversed. That is the only difference. But by convention, we usually perform phase diagrams using the more volatile component, or the composition of the more volatile component in the x axis, and accordingly we plot either p in the y axis or t in the y axis or y1 in the y axis. Now under this condition, we always find that y1 is always greater than x1 as expected, because we are dealing with the more volatile component, right. Now in this particular case, I can just mention in this case Pi, this is equals to Xi Pi saturated, or in other words, for two component mixtures I can write down the ratio of their partial pressures as P2 saturated X2 by P1 saturated X1. Now this particular ratio, this P2 by P1, this is known as alpha, which we define as the relative volatility. What is this relative volatility? It is the relative escaping tendency of the second phase with respect to the first phase, right. So therefore this is the relative escaping tendency of phase 2 compared to phase 1, right. So therefore this is termed as alpha. So therefore we can write this down as alpha into x 2 by 1 minus, or alpha into x 2 by 1 minus x 2, we can write it down in this particular term, from where we can find out that y, sorry, this is y 1, nothing, let it be y 2, does not matter. From here we find out that y 1 by 1 minus y 1, this is nothing but x 1 by 1 minus x 1, p 1 saturated by p 2 saturated. From here what do we get? We get y 1 equals to alpha x 1 by 1 plus alpha minus 1 x 1. From where we know that y 1 will always be greater than x 1, right. And therefore, we find that we always get a plot which is sort of a hyperbolic curve, and for all particular cases except for x 1 equals to 0 and x 1 equals to 1, y 1 will always be greater than x 1. Well, so till now what are the things that we have done? We have plotted the, we have discussed ideal solutions, we have discussed the Lewis-Randall rule, we have developed the Raoult's law from the Lewis-Randall rule, we have discussed under what conditions ideal solution model can be applicable. We have also discussed under what are the properties of ideal solutions, no heat or absorption or evolution, etc., etc., increase in randomness of mixing quite naturally, otherwise they will not mix spontaneously. And then we have discussed different phase diagrams for binary ideal solutions. The vapor and the liquid phases both exhibit ideal solution model. Well, I had also discussed how to construct the pxy txy diagrams, and in the next few slides I have just noted down the procedure for finding out the dew point temperature and also the bubble point temperature, etc. So, these procedures can be followed and different problems can be dealt with. The different problems are given at the end of this particular lecture series. So, you can try out these problems, 1 or 2 problems I have already done before you. You can try out the other problems, and in each problem we find that the answers are also provided for your benefit. Now, there is one particular type of your problem which we have not dealt with till now, which I would like to deal. These problems are known as flash calculation problems. What are these? Very frequently we encounter a situation where we find that more or less we introduce any particular feed. It can be a vapor feed, it can be a liquid feed. Since we just to make matters general, I would like to mention the feed composition as ZF, right, and then it is introduced into a partial vaporizer or a partial condenser, whatever the case may be. From here what do I get? I get, it flashes, I get a vapor stream with the amount of vapor formed is V moles, the composition is given by Y, and the pressure and temperature. I also get a liquid stream which again with the total fraction or rather total moles of liquid being L, the composition X, and temperature and pressure conditions. So, from here what I have done, I have just flashed any particular liquid or a vapor mixture for partial separation into a vapor stream and a liquid stream. For this case, from the overall material balance I know this, and I also know from the component material balance ZFI equals to LXI plus VYI, right. Now, and with this we also know the equations YIP equals to XIPI saturated, or in other words this this can be written down as KIXI, where KI is nothing but PI saturated by P, right. So, therefore, I have these two equations and I have got a set of K I equations as we say it. From there we can find out X I as Z F I. You can just calculate this and find out this is equals to L by F plus 1 minus L by F into K I. So, in this particular case usually what are known, we know pressure, we know temperature, we know the composition of the feed. And what are we required to find out? We are required to find out composition in the liquid phase, composition in the vapor phase, amount of liquid formed, amount of vapor formed. So, how do we proceed in this particular case? We know the temperature. Once we know the temperature, we can find out each Pi saturated, agreed. Once we know the Pi saturated, we know the pressure, then from there we should be able to find out Ki. Ki is Pi saturated for P. So, for each case we can find out the Ki's. Once we can find out the Ki's, then what we do? We guess either a L by F or a V by F, whatever it is. If we guess it, we can find out Xi. We can find out Xi for all the components I, fine. And then once we have calculated Xi's for all the components, we then check up Xi equals sigma Xi equals to 1. If we find it is not equal to 1, then again we start with a different assumed temperature, continue the process till we get Xi equals to 1. So, if we get sigma Xi equals to 1, we know that my guess temperature is correct and I have come or I have reached the correct mole fractions in the vapor liquid phase. Once I have done this, then from there what I do? I find out Yi's for the individual components. So, in this particular procedure has also been written down here. So, accordingly we can perform these particular equations or rather these calculations, and we can perform a few flash calculations in this way. There are a few problems which have been given at the end of the assignment. I guess there is one problem of pentane, hexane and heptane. This is the problem, right. So, in this particular problem also, suppose we find that these three they form the ideal condition, okay, and this is given. I think this is not this is the problem, I believe. Yeah, this is the problem. In this particular case, the way I have told you, the compositions are given, the ZFs are given. So, therefore, ZF1 this is equals to 0.2, ZF2 equals to 0.35, ZF3 equals to 0.45. We note that the Z's are actually X's here because we introduce a ideal, rather we introduce a liquid solution here. The temperature is given as 95 degrees centigrade, the pressure is given as 150 kPa. So, what are we required to find out? We are required to find out Xi's and Yi's, right. So, what we do? Again the way I have said, T equals to 95 degrees centigrade, I calculate the P1 saturated, P2 saturated, P3 saturated in this particular case from the Antoine's constants. The Antoine constants you can note down the A, B, C. For this case, for pentane is my component 1. So, for this case A is 6.876, B is 1075.78 and C is 233.205. For N hexane we find this is 6.91, 1189.64 and this is 226.28. For N heptane, what do we find? N heptane this is 6.894, 1264.37, 216.64. So, from here we can find out the P1 saturated, we can find the Pi saturated. We find that this is 3967.8 torr, this is 1613.5 torr, this is 686.6 torr. We know the pressure, the total pressure, it is 150 kBA. So, therefore, we can find out the Ki's here. What are the Ki's? In this case, it is 3.5266 and then this is 1.4311, this is 0.6103. So, once we have done it, we can find out the exercise, right. For finding out the exercise, we need to guess L by F. Say suppose I start with my first guess of L by F as 0.121 and find out the corresponding xi. Say in this particular case, suppose I start with 0.121, my x1 will be equal to 0.0621 and accordingly my x2 will be 0.2533, x3 is going to be 0.6845. More or less my sigma xi is 0.999, which I can take as 1 in this particular case. Accordingly, I find my yi's. The yi's in this particular case, if I write it down here, the yi's will be 0.219, 0.3633 and 0.4178. So, therefore, the fraction which was vaporized 1 minus L by F, this is nothing but equal to 0.879. A few other problems have also been provided here. You can try out the problems. So, in this particular class, what have I done? I have discussed different problems of concerning ideal solutions. For example, I have discussed if Px is given, how to find out Ty, if Py is given, how to find out Tx, if Tx is given, how to find out, if Px is given, how to find out Ty, or if Py is given, how to find out Tx. And I have also discussed flash distillation problems. There are a few problems which are there in this particular slide. The answers are provided, you can work them out to have more feel of ideal solutions. Now, suppose we go to the next part of our lecture, which deals with non-ideal solutions. What do you expect for what is going to happen for non-ideal solutions? What are the things that we expect in this particular case? Let us see. So, in non-ideal solutions, let us see what happens. In ideal solutions, I have already drawn this particular case. We have, what did we find? We have found that for ideal solutions, the partial pressure and the total pressure, they vary linearly with mole fraction. Definitely, if the solution does not behave ideally, and along with that, what are the other things that we have found? We found 3 features of ideal solution. First feature is that partial pressure and total pressures, they vary linearly with mole fraction. Number 1. Number 2, we have observed that delta Vm equals to 0, delta Gm equals to RT sigma xi ln xi, and delta Sm was equals to minus R sigma xi ln xi. These are the things that we observed. If it is non-ideal, then definitely there will be some evolution or absorption of heat, and when the two components mix, then definitely we expect that either there will be contraction in volume or there will be expansion in volume. So, therefore, what do we expect? We expect that this might be not equal to 0, this might not be equal to 0, and so if these one of these are not 0, then naturally this again becomes not equal to 0, etc., etc. It continues in this particular way. Now, remember one thing, non-ideal solution can have only one particular property different. For example, it can have delta Vm not equal to 0, while the other characteristics, they follow the ideal solution model. Okay, it can happen, or it can happen that maybe more than one particular characteristics are not being exhibited by the non-ideal solution. So, therefore, for non-ideal solution, firstly, if these things happen, then quite naturally your pressure cannot vary linearly with xi. It is going to deviate from this, and the deviation can be either way. We can find that the pressure is actually higher than the, there can be two things. One is the pressure can be the vapor pressure can be higher than that calculated from the ideal solution model. It can be same for all the cases. And accordingly, since this happens, so naturally the total pressure will also be higher as compared to the total pressure calculated from your ideal solution model. So, therefore, in this case, what do we say? We say that this exhibits positive deviation from Raoult's law. We can also have other thing. We can see that moment we mix the two components, what happens? There is a contraction in volume. It can happen, and under that case, what do we find? Suppose, see, it all depends upon the interaction of the molecules. Repeatedly I have said that when we assume that the interaction between like and unlike molecules are the same, then we have ideal solutions. Suppose we see that the interaction between unlike molecules is greater than the interaction between like molecules. Then what happens? Then in that case, when we mix, then the interaction it increases. When the interaction in the liquid phase increases, naturally the tendency to go into the vapor phase that decreases, and under that condition, what do we have? We have a negative deviation from Raoult's law. In every case, we are going to have a negative deviation from Raoult's law. And when we find that the intermolecular interactions between unlike molecules are less as compared to the intermolecular interactions between like molecules, then when we mix, then what happens? They are not very comfortable, so there is a greater tendency of vapor formation. So, as a result, the saturated pressure becomes higher as compared to that calculated from the Raoult's law. So, therefore, we have a positive deviation. So, when the unlike interactions are less as compared to the like interactions, we have positive deviation from Raoult's law. When the unlike interactions are higher as compared to like interactions, we have negative deviations from Raoult's law. The entire thing can be summarized by a formula which has been provided by Van Laar. Now, this particular person, as we know, that he has worked throughout with solutions, and he has proposed a formula which accounts for, or rather which combines, he has proposed a formula which combines Raoult's law and deviations from it. What is the formula that he has given? It's quite an interesting formula. He suggests P2 it is equal to X2 P2 saturated, which is Raoult's law, with a correction factor as exponential 1 minus X2 whole square delta U0 by KT, right. For what is delta U0 equals to? Delta U0 is the interaction energy. Interaction energy which takes into account the differences in nature of the interaction of like and unlike molecules, right. So, therefore, in this particular equation, if I write the equation once more here just to define all the properties, it is the correction term to Raoult's law is 1 minus X2 square delta U0 by KT, where K is nothing but the Boltzmann constant, T is the temperature as we all know. This is the temperature, and this delta U0, this is the interaction energy. This takes into account the differences in nature of interaction between like and unlike molecules. Now, when delta U0 equals to 0, then naturally we find that interaction between like and unlike molecules similar. So, therefore, the exponential term it becomes almost equal to 1, and P2 can be given as X2 P2 saturated, which is the case for ideal solution. When we find that delta U0 is greater than 1, Under that condition, we get positive deviation from Raoult's law. And when does this happen? This positive deviation happens when unlike this happens when unlike molecules attract more weakly as compared to like molecules, right. Under this condition, as I have explained, so therefore, evaporation is facilitated and vapor pressure is higher than that calculated by Raoult's law. And if delta U0 is less than 1, then in that case, as I have said, at unlike molecules attract more strongly, and so therefore, the total molecular interaction increases and the evaporation of molecules becomes more difficult, and we have negative deviations from Raoult's law. So, therefore, we can have two type of deviations from Raoult's law. Now, what to do under this case? If we have some deviations, what is the thing, how are we going to account for the deviation? For everything, you will notice that we take help of, or rather we go to our ideal the gas state and try to find something. In the gas state, what did we find? We found PV was equals to RT for 1 mole of gas. Definitely, most of the gases, they were not ideal, and as I had mentioned, we had introduced a compressibility factor to account for non-ideal behavior. So, in this case also we found that for ideal solutions, this is the situation. So, therefore, when it is not ideal, people thought, why not introduce a correction factor here, such that this correction factor would take into account the deviations from ideality. And the correction factor which was introduced here, that is known as the activity coefficient. And this particular correction factor, they found that this gamma I can be greater than 0 for this particular case. Here gamma I should be greater than 0, here gamma I should be less than 0, right. So, therefore, what are the things which happened when a solution does not behave ideally? There are two things. First thing is, we find that there is either positive deviation or negative deviation from Raoult's law. So, therefore, we find that in this particular case, the linearity is not followed, and this is modified by introducing a gamma I here, where we can write down P I equals to gamma I x I P I saturated. So, therefore, the equation for non-ideal case, it becomes this. Along with that, what happens, just the way I have written down, there are some volume changes of mixing. Definitely, under that cases, we will not have delta m equal to 0, we will have some delta m delta Vm, which may be either greater than 0 or it may be less than 0, but it will not definitely be equal to 0. And this excess property which the solution has, just because it is not ideal, is known as the excess property of the solution. So, therefore, with advent of non-ideality, what are the things that we have come across? We have come across an activity coefficient, and we have come across another set of properties which are known as the excess properties, something similar to concept as the departure functions or the residual properties which we had described for real gases. You will remember, under that condition, the residual properties was real gas value minus the ideal gas value. In this case, the excess property, suppose it is, we denote it as m excess, it is the m real value minus the m ideal value. So, the property in the real solution minus the property in the ideal solution. Again, when we have defined a set of property excess properties, we have total excess properties which will be given by capital letters with a superscript e. We will be having naturally when we have excess properties, all of these are extensive. We will be having molar excess properties which will be given by a small case letter, and very sadly we will also be having a partial molar excess property which will be given by this particular set. And we will also find out that just the way of total properties, molar properties, in this case also they obey all the equations which are applicable for molar properties and total properties. For example, in this particular case also we will have U excess equals to H excess minus P V excess. We will have G excess equals to H excess minus T S E excess, and so on and so forth. So, in the next class what we do? We deal with non-ideal solutions, and for dealing with non-ideal solutions we will be dealing with excess properties, and we will be dealing with activity coefficient, and we need to remember that the activity coefficient has come up because the solution is not ideal. The excess properties have come up because the solution is not ideal. So, therefore, there should be some relationships between the excess properties and the activity coefficients. So, in the next class we will be trying to establish relationships between activity coefficient and excess property, and since we have defined a new property gamma I, we would like to find out how gamma I it varies with temperature, pressure and composition. We would be deriving an equivalent Gibbs-Duhem equation for gamma I, and then we would like to find out how we can determine gamma I from known experimental parameters, because finally the prediction of gamma I would help us to calculate the fugacity in the liquid phase, from where we can proceed for further phase equilibrium problems in non-ideal solutions. So, we enter into the domain of non-ideal solutions in the next class, and it will make your journey of thermodynamics slightly more difficult, but I hope you will be enjoying it with us. Thank you very much.